Sequences and series can be made to be pretty confusing and they get pretty complicated. But if you just remember at their core, sequences are just lists of numbers separated by commas, and series are those same lists of numbers separated by plus signs because we're going to add all those numbers up. We're going to start today with talking about two different ways that you can write rules for sequences, recursive rules and explicit rules. There's a lot of new notation that comes along with sequences and series, so this video is going to focus a lot on that, and we'll also get into some basic arithmetic and geometric sequences towards the end. So recursive rules will always have two parts to them. They'll always have a rule and a starting value. So like in this example, our starting value a sub 1 is 2, and then the rule to follow is this: a sub n plus 1 equals a sub n minus 3. So a sub 1 is how we represent the first term, and we're saying that the value of that first term is 2. So if I was going to write this list out, the first number would be 2. So a sub n plus 1, that means the next term, because this would mean the current term. That's because n is the term number, so if you take n plus 1, that's going to be 1 more than the current term number, that would be the next term number. And I just want to point out the difference between when I say term number and term value. So term number, that's like how far along you are in the list, and the term value, that's the actual value of the number in that list. So this is the rule. It's telling me in order to get the next term, take your current term and subtract 3 from it. So I have 2 currently. If I want to know the next term, I just take the current term and subtract 3 from it. If you do that, you get negative 1. So if I want to know the next term, I would just take the current term, now it's negative 1, subtract 3 from that again, and you get negative 4. And you could keep doing this. If you subtract 3 again, you'd get negative 7. And this list would go on forever. So in recursive rules, the variable that you're plugging things in for is just the current term. You're always plugging in the current term, and the output you're getting is the next term. Recursive rules kind of remind me of like following a train down a track, but you're placing one piece of train track down at a time to reach the final destination. So it's not really efficient. Like if I wanted to know the 50th term, I wouldn't be able to find that unless I knew the 49th term. And I wouldn't be able to find that unless I knew the 48th term. So it's just one piece at a time. It's really inefficient. Whereas the explicit rules tell you exactly the value of whatever term you're looking for. This is going to tell me the value of a sub n, which is any term, and I just get that by plugging in some n value. So the input is the term number, and the output is the term value. If I wanted to know the 50th term, like a sub 50, I would just plug in 50. So negative 3 times 50 plus 5, which would be negative 150 plus 5, which would be negative 145. I got that really quick, whereas over here I would have had to figure out all 50 terms leading up to that. So we'll call this the nth term, and we'll figure it out by plugging in some different n values. Let's figure out the first few numbers in this sequence. Like the first term is when n equals 1. If I plugged 1 in here, that would look like negative 3 times 1 plus 5, which would be 2. If I plugged in n equals 2, that would tell me the second term, so that would look like negative 3 times 2 plus 5, so that'd be negative 6 plus 5, which would be negative 1. If I plugged in n equals 3, that would tell me the value of the third term, and that work would look like negative 3 times 3 plus 5, so negative 9 plus 5, which would be negative 4. And let's just do one more. If n equals 4, we could plug 4, and I'll do that over here. So negative 3 times 4 plus 5, so this would be negative 12 plus 5 would be negative 7. So actually you can see this sequence we just came up with is the same one as we came up with over here. So this recursive rule and this explicit rule are representing the same list of numbers, they're just written differently. So let's look at 2 more examples. Here we have another recursive rule. It says a sub n plus 1, so that's the next term. In order to get the next term, you have to take the current term, multiply it by 2, and then add a sub n minus 1. Well, if n plus 1 means the next term, n minus 1 means the previous term. But this isn't enough information, because remember, recursive rules have to tell you like starting points. Like in this case, I know what to do. I know to take 2 times the current term and add the previous term, but I don't know what the current or the previous terms are. So in this case, we'll have to specify where the list is starting. Let's just say a sub 1 equals 2, just like it was in the first example. But then we actually have to go back and define what a sub 0 is, because we need to know the current and the previous term. Let's just say that a sub 0 is 1. Now, the directions said to write the first 5 terms defined by the rule, so I'm going to start my list with this a sub 1 value, and there's going to be my first 5 terms. I'm not going to include this because it says a sub 0, but I still need to use it when I'm calculating this next term. So let's get this next number by taking 2 times the current term, so 2 times 2, and then add the previous term, which was 1. So 2 times 2 is 4, plus 1 is 5. So a sub 2, my next term, is 5. If I want to get the next term, take 2 times the current term, so I'll write 2 times 5, and then add the previous term, which in this case was 2. So 2 times 5 is 10, plus 2 would be 12. And that's a sub 3. If I want to get the next term, take 2 times the current term, 12, and add the previous term, which was 5. So 2 times 12 is 24, plus 5 is 29, and we'll do one more. So that was a sub 4, we'll end on a sub 5. So 2 times the current term, 29, but then we have to add 12 to that. This would be 58 plus 12, which was 70. But again, you can see if I wanted to know what is the 50th term, like a sub 50, that would be kind of annoying because I'd have to figure out a sub 49, a sub 48, and all the way back I'd have to figure out every term in that. Explicit rule is a lot nicer to work with because it just tells us a sub n is this. Just plug in whatever term number you're looking for and it'll tell you the value. So if I want to know a sub 1, or in other words where n equals 1, the first term, I'm just going to plug 1 in. So 1 plus 2 over 1, that would be 3 over 1, and I'll just write 3. For a sub 2, or in other words where n equals 2, the second term, I'll just plug 2 in. So 2 plus 2 over 2, so that would be 4 over 2, which I can simplify to be 2. A sub 3, where n equals 3, that's the third term, I'll plug 3 in. So 3 plus 2 over 3. And that would be 5 over 3, which I can't simplify, but I'll just leave that as 5/3. For a sub 4, that's the fourth term, that's where n equals 4, I'll plug in 4. So 4 plus 2 over 4, that would be 6 over 4, which could simplify to be 3 over 2. And we just got one more, a sub 5, that's where n equals 5, that's the fifth term. So 5 plus 2 over 5 equals 7 over 5, and I'll leave that as 7/5. So the sequence does follow a pattern. It's pretty easily represented by this explicit formula, a sub n equals n plus 2 over n. It does follow a pattern, but if I just showed you this list of numbers, it would probably be hard to figure out what that pattern is. Same thing over here. If I showed you this list of numbers, it'd be hard to figure out what the pattern is that we're following. Luckily, most of the sequences and series we study are called arithmetic or geometric, which just means we're going to add or subtract by the same value repeatedly, or we're going to multiply or divide by the same value repeatedly. So let's take a look at arithmetic and geometric sequences. Arithmetic sequences are the type that will either add or subtract the same value every time, and that value is referred to as d for common difference. So by saying common difference, it kind of sounds like we're going to subtract all the time, but in this case d is positive 3, so we're going to be adding 3. This first example also tells us that a sub 1 is 17. So if I wanted to start writing this list out, I would start with 17, and then I would just be adding 3 every time. So 17 plus 3 gives me 20. If I add 3 again, that would be 23, 26, and 29. And again, this could go on forever. So I'll represent that with 3 dots here, but I don't want to write this list out forever and ever and ever. I want to represent it completely with just a recursive rule. So remember, these always have 2 parts. They'll always have a starting point and a rule to follow. Well, I know a sub 1 is 17. That's from up here. They already told me that. And then I just have to write out the rule. And the rule is just to keep adding 3 over and over. Take your current term, add 3 to it, and that's the next term. So let's write all that out with our math notation. Like to get the next term, a sub n plus 1, we take the current term, a sub n, and we just add 3 to it. And there's your recursive rule. So instead of writing this infinitely long list, you can represent all of those numbers just by writing this rule out. But remember, recursive rules are kind of annoying to work with because you have to get every term one number at a time. With an explicit rule, we could just plug in the term number. So let's write that out as well. These are a bit tougher to think about, but they're much nicer to use. Remember, these are just going to tell me the value of whatever term I want. So I'm just going to write a sub n equals, and then I have to figure out, like, how could I plug n in to figure out these different term values. So just like before, I'm actually going to just start with my first value. I'm just going to put 17 here. Since we're starting there, it's kind of like every future value depends on that 17. So I'll start the sequence with 17, and then I know I'm going to be adding 3 to it, but I'm not sure how many times because I'm not sure what term number I'm looking for. So if I wanted to find the second term number, I'd want to take 17 and add 3 just one time. If I wanted to find the third term number, I'd have to add 2 of these differences. If I wanted to find the fourth term number, I'd have to add another difference, so there'd be 3 of them. If I wanted to find the fifth term number, I'd have to add another difference, there'd be 4 of them. It seems like whatever term number I'm looking for, I just add 1 less than that number of differences. So I'm going to get rid of all those 3's, and I'm just going to write n minus 1. That means whatever term number you're looking for, just subtract 1 from it. That's how many differences you'd have to add to the first term to get there. Think about if you wanted to get to the 10th term, and you were starting at the first term. How many jumps would you have to make to get from term 1 up to term 10? You'd have to go up 9 times, right? So 10 minus 1 is 9. Now, we could just leave this how it is and call that our final answer, but we can actually make it a little bit nicer just by distributing this 3 in. So we get 17 plus 3n minus 3, and then I have a 17 and a minus 3 that can go together, so that would be 14 plus 3n. And I'm just going to rearrange it so it's the 3n first plus 14. Because now, if you look at this a little bit differently, you could almost think of this equation as like y equals mx plus b. If you thought of this as m, that would be like our slope. And that's what's happening because we have a common difference of 3. Every time we go up one term, we're going up 3 units. And then this is kind of like our starting point. I know the starting value in the sequence is 17, but if you thought about going back to like a sub 0, that would be kind of like the y-intercept, and in this case it'd be 14, because to go backwards you'd want to subtract 3. So arithmetic sequences should kind of remind you of linear functions. And that common difference is kind of like our constant rate of change. So let's take a look at another example. Here they're telling me that a sub 1 is 2. The value of my first term is 2, and the value of my 12th term is 46. So I'll jump over here and say that n equals 12. That would mean this is a sub 12, and the value of that term is 46. So let's see if we can fill out the rest of this sequence. Since I know this is going to be arithmetic, I know we're going to have some common difference. So let's see, if I started at this first term, I would have to add some common difference a bunch of times to get all the way up to the 12th term. I'm actually going to write out a little equation. So I'm going to say 2 plus whatever this difference is, and how many differences would I have to add? To get from the first term to the 12th term, I'd have to make 11 jumps. So I'll say 11d equals, and then that's going to get me the term value 46. If I start at this term value and add the difference 11 times, that'll get me to the value 46. So now I can totally do this because I just have to solve this for d, so I'll just subtract 2 from both sides and I get 11d equals 44, and then after dividing, you'd see d equals 4. So let's add 4 to get the next term. 2 plus 4 would be 6. If I add 4 again, that would give me 10. If I just keep adding 4, so let's see, this would get me to 14, and then 18, and then if you just kept adding 4, eventually you'd get to 46. So let's write our recursive rule for this so that we can represent the entire sequence with just a rule. Remember, it has to tell us our starting point, which was 2, and then a rule to follow. To get the next term, a sub n plus 1, we just take the current term, a sub n, and what do we do to it? In this case, we were adding 4 every time, so plus 4. And there's your recursive rule. For the explicit rule, I want to find out just whatever the term value is for any nth term. So I'll say a sub n equals, and then I want to just be able to plug in n. So just like we did in the first example, I'll start with my first value, 2, because remember, every term value after that depends on the first value, 2. So we'll say 2 plus, and I just kept adding 4 over and over. And remember, to get to to get from the first term to the 12th term, I had to add 11 differences. It's always 1 less than the term number, so n minus 1. But then let's just simplify that. So if I distribute the 4 in, that would give me 2 plus 4n minus 4. And then I can put the 2 and the minus 4 together. That gives me negative 2 plus 4n. And then one last step, I'm just going to rearrange it. So a sub n equals 4n minus 2. And there's your explicit rule, simplified completely. So these examples were both arithmetic, this is where you're adding or subtracting the same thing, but we can also have geometric sequences where we're multiplying by the same value every time. For geometric sequences, we have some r value, that stands for common ratio. So we're going to be multiplying or dividing by this common ratio. So let's start the list out just by writing 5 for our first term, because that's what they told us here, a sub 1 equals 5. And then to get the next term, I'm going to multiply by this 3 halves. So 5 times 3 halves. And I'm just going to write that as 15 over 2. If I multiply by 3 halves again, well, 15 times 3 is 45, and then the bottom would be 4. 2 times 2 is 4. Multiplying by 3 halves again, 45 times 3 is 135 over 8 this time. And then the last one, I got to multiply by 3 halves again. So 135 times 3 would be 405, and then 8 times 2 would be 16. So these numbers are getting kind of obnoxious to work with. So let's just write our recursive rule. And that'll define this entire infinitely long list. Remember, it can go on forever, but it'll define the whole thing with just one simple recursive rule. So again, we'll start with a sub 1, which they already told us is 5. I just have to write the rule. So a sub n plus 1, the next term, and in order to get that, you take the current term, so a sub n, and what do you do to it? You just keep multiplying by 3 halves. So I'm going to take a sub n and just multiply by 3 halves. If I wanted to write the explicit rule, remember I don't have to give us a starting point because you could just plug 1 in to find the first term. We just have to write the rule for any term, so a sub n. Now let's think of this just like we did with the arithmetic sequences. We started with our first term because everything after that does depend on that first term. So we'll start with 5, and then we were taking that 5 and we were multiplying it by 3 halves over and over again. And we're going to multiply it by that n minus 1 times. So remember, if you started with your first term and you wanted to get to the 5th term, you'd have to multiply by that common ratio 1, 2, 3, 4 times. That's 1 less than the term number you're looking for. So that's why it's n minus 1. Now with this explicit rule, there's actually nothing for us to simplify because this exponent can just stay how it is, and we can't combine these numbers because the 3 halves has an exponent on it and the 5 is just being multiplied out front. So that's our final answer. Now if you think about what this function looks like, it's got some starting value and then it's just a base raised to an exponent. Hopefully this reminds you of an exponential function. And we already know a little bit about exponential functions, like we're familiar with exponential growth and decay, so that might help us with these sequences. In this last example, we have just one more geometric sequence, but they've just given us the 4th and the 7th terms. So term 4 is negative 18, but then I have to skip all the way over to term 7 and say that term 7 is 2/3. So it's kind of weird that they gave us values kind of in the middle of the sequence. We don't even know where we're starting, but we can still say that negative 18, if I multiply that by some r value a bunch of times, eventually I will get to the value of 2/3. And how many times would I have to multiply by that r value? Well, to get from the 4th term to the 7th term, I'd have to go up to the 5th term, the 6th term, and then the 7th term. So I'd have to make 1, 2, 3 hops. So I'm going to multiply by r 3 times. So if you just divide out that negative 18, you'd actually get r equals negative 1 over 27. And then you'd have to take the cube root of both sides. And then you get r equals negative 1/3. So that just means I'm going to multiply by this negative 1/3 over and over again. Let's just see if that works. If I take negative 18 and multiply that by negative 1/3, that would give me positive 6. If I multiply that by negative 1/3, that would give me negative 2. And then if I multiply that by negative 1/3, that would give me positive 2/3. Yeah, so that worked out. All right, now if I want to go backwards, instead of multiplying by 1/3, I'd be dividing by negative 1/3. That's like multiplying by negative 3. So here I get 54. If you multiply by negative 3 again, that would be negative 162. And you could multiply by negative 3 again, and this time it would give you positive 486. So there's the first little bit of the sequence, and remember it could go on forever. I could write comma, dot, dot, dot. So let's represent all this a little bit more efficiently by writing a recursive rule. Recursive rules always have to tell you where to start, and so this problem didn't tell us where to start. We actually had to figure that out ourselves, and we got 486. So there's our first value. Every term number after that depends on 486. So we'll say the next term, a sub n plus 1. In order to get that, you take your current term, and what do you do to it? Well, working forwards here, we were multiplying by negative 1/3. So we'll say times negative 1/3, and there's your recursive rule. So let's just wrap this up by writing an explicit rule, and this will be the most efficient way of writing this sequence. So we don't have to say where to start, we just start writing the rule, a sub n equals. Just like before, we'll start with our first value, 486, because everything else depends on that. But then what are we doing to it? We're multiplying by negative 1/3 over and over again, and the number of times is n minus 1. So you raise that to the n minus 1 power.